Good afternoon. Welcome to the brave souls who decided to stick it out today for the Walls Lecture. It's my privilege to introduce to you today our speaker, Dr. Eva Harris, who is currently a professor in the Division of Infectious Diseases in the School of Public Health and the director of the Center for Global Public Health at UC Berkeley. Dr. Harris received her BA in Biochemical Studies from Harvard University and a PhD in Molecular and Cell Biology at UC Berkeley. And as a faculty, she has developed a multidisciplinary approach to study the molecular virology, pathogenesis, and epidemiology of dengue, the most prevalent mosquito-borne viral disease in humans. Dr. Harris has been studying global health before the word global health was even invented. Her fieldwork focuses on laboratory-based and epidemiological studies of dengue and influenza in endemic Latin American countries, particularly in Nicaragua, where she maintains a field site. In 1997, Dr. Harris received a MacArthur Genius Award for her pioneering work over the previous 10 years developing programs and working to build scientific capacity in developing countries to address public health and infectious disease issues. To continue and expand this work, in 1998, she founded a nonprofit organization in San Francisco, Sustainable Sciences Institute, and published a book on the subject with Oxford University Press. She's been a co-director of the Fogarty International Center's ITRIAD program from 1997 to 2003, and is a real Renaissance woman in terms of her other activities as well. We hear that she's a great salsa dancer. So today we're going to hear from the bench to the field and back, a global approach to dengue and influenza. And following the talk, I'd like to remind everyone that there will be a reception. Thank you. Dr. Harris?
Thank you, Mark. Okay. Thank you very much. I'm so impressed. I really thought this was going to be me, myself, and I, although it actually hasn't started snowing yet, so I'm kind of perplexed at the panic that has ensued, being a New Yorker myself. But anyways, so thank you very much, and we're going to have a fun-packed afternoon, mostly because I didn't have an opportunity to trim my talk because I was so excited talking to these wonderful colleagues that I've been able to spend some time with this morning and early afternoon. And so what I'm going to do today is tell you about an approach which I've been kind of building over the last 20, 25 years, which has to do with combining basic science approaches with work in the field, which these days is now called global health. I used to try and come up with words before that existed, and I used to call it international science. But we'll see what the main idea here is that I'm going to tell you about dengue, and then I'm going to tell you about our work that essentially spans from the molecular virology through animal models and immunology out into clinical and epidemiological and community-based studies. And what I'd like to do is to kind of weave a story starting in the field and with our work in dengue, and then show you how that led us into work on influenza, and then some hypotheses that we're now bringing back to the lab. And then we're going to move into a mouse model that we've built that has then generated hypotheses which we're now bringing back to the field. And then at the very end, actually, we're going to go to Managua, Nicaragua, and I'm going to show you a little bit about how our work has expanded beyond the scientific enterprise that I initially started with, and is actually moving into other areas of public health to serve the country of Nicaragua by the Nicaraguans themselves. And I think we'll end on that note. Okay, so dengue is a real problem because there's, as you'll see, many millions of people are affected every year, about up to 40 million cases annually of what we call dengue fever. But there's also a much more severe form, which is life-threatening and can cause a plasma leakage syndrome that can kill the patient within 24 to 48 hours. And the big problem is that we just don't know who of these 50 million people is going to end up like this. And that's a very strong pediatric disease, although as it moves into new areas, also affects adult populations. So in terms of the clinical features, I've had it actually, I can tell you all about this, but there's a very high onset fever, abrupt onset fever, muscle or bone pain called myalgias and arthralgias, retroorbital pain, fatigue, and it's just a really nasty, it's called la quebradora, or breakbone fever. And what happens, though, is that there's a series of what we call warning signs, then there's severe dengue, which until recently has been known as dengue hemorrhagic fever and dengue shock syndrome, which is the real point about it is this increased fluid leakage, which then can lead to hypovolemic shock and death if appropriate fluid management doesn't occur. So the really interesting thing about dengue is that if you can catch these warning signs in time and replace the fluid judiciously, then the person can walk out of the hospital 2 to 3 days later with no sequelae, essentially. But if this is not recognized in time, then they can die. And if you don't get it in time, then the shock is no longer able to be resuscitated. So it's a very intense disease at the public health level and at the medical level. It's associated with internal bleeding, low platelet counts, increased serum cytokines, and as I mentioned, this shock syndrome. So in terms of who spreads this, in the Americas, it's mostly this Aedes aegypti mosquito. There's a lot of interesting past about this mosquito because it also transmits not only dengue virus, but also yellow fever virus. And so there was a lot of eradication campaigns that happened during the 1950s and 60s in the Americas, which, because of the threat from yellow fever, which wiped clean the Americas for as long as the money was there to support the program. And then as soon as the program disappeared, immediately there was reinfestation by Aedes aegypti and dengue on its heels. And so one of our projects is actually around looking at sustainable ways to involve communities in the control of dengue and its vector. In Asia, the tiger mosquito called Aedes albopictus is more important as a vector. Aedes aegypti tends to be the epidemic vector and albopictus to kind of the interepidemic periods. So in terms of the disease period, so every infectious disease has this pyramid where you have fewer severe cases, and then here we have these tens of millions of estimated cases, and as I'll show you, there's even more cases that are unreported, and then we have all the asymptomatic infections. So the curious thing about dengue is that usually with an infectious disease, if you've survived the infection and ideally had an asymptomatic infection, then that's good because you're supposed to be immune for life. The problem with dengue, as you'll see in a moment, is that there's actually 4 flavors or 4 serotypes, and it turns out that having a second infection with a different serotype is the greatest risk factor for severe disease. So in fact, instead of being a good thing, having an asymptomatic infection actually puts this entire set of the population at risk for this more severe disease. So instead of only worrying about this part of the pyramid, now we're really worried about the entire bunch, which is a very large number of infections. So the deal with dengue is that it has this alarming spread over the last couple decades on 3 different levels. There's a rapid number of cases that are rising, an aggressive geographic spread, and then this co-circulation of the 4 serotypes. So there are 3 different elements that are all converging during this last couple decades to really get us worried about it. Now this is where dengue is spread across the globe. It's essentially like a subtropical, tropical belt, if you wish, including actually the southern parts of the United States. And just so you don't feel left out, this is where the vector is present in the United States. And in fact, in Washington, I just actually gave a series here, the Howard Hughes holiday lectures. The children actually found Aedes aegypti, albopictus in their own backyards and grew them up, and we studied them together. And so there you go, you're not immune. And in fact, this year there was this Key West outbreak, which some of you might have heard about, where there was about 56 confirmed cases in Key West, but actually when they went back and did a serological survey, there was a lot more people that had been infected than anyone had ever imagined. So, and actually, sorry, I tend to tell these little anecdotes, but the dengue and yellow fever were a huge problem along the whole eastern seaboard in the 1900s, 1800s and 1900s, and it was actually, there's this great book by Andy Spielman called Mosquito, and he describes these scenes from Philadelphia, where it was literally like Monty Python, bring out your dead. I mean, there was this yellow fever, people would just run screaming from the cities, and there's a lot of history around exactly yellow fever and dengue in the United States, and it wasn't until the essentially use of air conditioning and screened windows and cleaning up waste and water management that ridded at least the eastern seaboard of dengue. So I told you about this global rise in number of cases. So here on the y-axis, We have the number of cases reported in millions, and you can see over here are the decades on the bottom, and you can see a cyclical pattern, but essentially it's going off the map, and we're way up here somewhere now. The other issue has to do with this geographic spread, and if I can make this thing work, we're going to try and show you this very nice stuff that was done for me by Howard Hughes, which shows you with actual data, with the red being the most number of cases, you can see that over the years how this has been spreading throughout the Americas. And again, it has that cyclical pattern, but you can see that as we get to more and more recent, we have more and more deep red, which is the spread of this throughout the Americas. Now, as I mentioned, so that's the second point. The third point is this question of the co-circulation of all of the different serotypes. And so here, as I mentioned, we have these 4 flavors shown in different colors, dengue 1 to 4. And in the 70s, for instance, we didn't have that much dengue, and where there wasn't that much co-circulation. But say in 2004, you can now see that all 4 serotypes are circulating in all places. And as we discussed previously, this is in fact a risk factor for the more severe form of the disease. Now you think, so it's very interesting in terms of why this emerged. Dengue, classic dengue fever, has actually been around for a very long time and is actually in ancient Chinese scripts, etc. As I mentioned, with the eastern seaboard of the United States. But it wasn't until the 1960s that this emerged as a really major problem, because hemorrhagic fever and shock syndrome, the severe forms, simply had not occurred prior to the 1960s, 50s and 60s. And the question was why? Well, it turns out that actually it grew in Southeast Asia. This DHF, DSS emerged because of the movement of troops and of ships during World War II. So the ships actually moved the mosquitoes around, and then the ships and the planes actually moved the soldiers carrying the virus, so then the virus also spread. So then you got this co-circulation of the virus with its mosquito vector. Now what's happening these days is actually not because of war, but it's just because of global trade and travel and urbanization. So what you see here is just a picture of the global trade, and this is actually a picture of a barge with used tires. And in fact, the reason that the United States was all red with Aedes albopictus was due to a point introduction in the 1970s in New Orleans of a boat with tires from Southeast Asia, and then the tire was water, and then the water was larvae, and those were the albopictus that actually spread throughout the United States. Now, global travel, I was going to say this looks like a day in my life, but this is actually, and most of you I'm sure, but this is really jet travel within a single day. And you can imagine that with all these people going all over the world this quickly, each of which could be viremic, it really is this hot zone scenario, and you can get spread very easily of dengue viruses. And then the last point is this urbanization. You can see here in different parts of the world, but we see 1950, 2000, 2030, and this is the percent that's going to be urban, and it's rising at a tremendous rate. And the way that this urbanization occurs is actually in a mostly unplanned manner in many marginalized tropical cities where there's poor waste and water management. And the poor water management means that you often have no running water or little running water, and so therefore people are storing clean water. And guess where Aedes aegypti likes to breed? Clean water. It's actually not in these dirty, muddy, nothing. It's actually clean water around people's homes. And then the other side of this is the poor waste management, which means that you have plastic containers and tires lying around which are capturing rainwater, and that's also one of the preferred breeding sites for Aedes aegypti. So the bottom line of all of this is that essentially dengue and its mosquito have adapted perfectly to our current status of human behavior and the human ecology. And that's what is driving this dramatic spread. So I mentioned that there's these 4 different serotypes, and why this is important is that we can have this person being bitten by a mosquito carrying dengue 1 in red, and so then this person will evolve an immune response. I'm here just showing antibodies, but of course there's a T cell and a B cell component to this immune response, and this will eventually clear the virus in a primary infection. So the virus is cleared, but the antibodies and the T cells remain. Now, upon reinfection with dengue 1, we believe that the person is protected and that the virus is cleared by that homotypic, as we call it, immune response. However, in a secondary dengue 2, or a separate virus, a distinct virus, what happens is the antibodies and the T cells only bind weakly and lead to an aberrant immune response, which actually enhances the disease and can make it worse. And so this is why sequential infections can lead to the severe disease. And a lot of my work, both in the mouse model and in the humans, has been directed to trying to understand why is it that in some cases you get protection and in others you get this enhanced disease. And so this is very complex because in addition to the human, the mosquito, and the virus, we have not only individual risk factors and then viral risk factors, but we also have this problem of what we call epidemiological risk factors, which has to do with the susceptibility of the entire population because of that interplay of the 4 different viruses. So it's only when you have all of these things happening, you get the perfect storm, and that's when you get the severe form of the disease. So with all of this complexity, I initially started about 15 years ago working on dengue and created a program that spanned from the molecular virology, where we study the viral replication and RNA structure and trans factors that interact at the protein level, and then a module on pathogenesis and immunology, where we've been building a mouse model and to understand the immunology and also to serve for preclinical research. Work on diagnostics, and then what I'm going to talk about today is, again, this epidemiology, our cohort and hospital studies, and a little bit about our work just to build scientific capacity. So I'm going to mention these 2 prospective studies of dengue that we have in Nicaragua. Nicaragua is one of the larger countries in Central America, and this is Managua, which is the capital, and we have a hospital study where we recruit children from 6 months to 14 years of age, and then, as you'll see later on, but we collect blood, which we have virus, antibodies, and peripheral blood mononuclear cells, or PBMCs. And then we collect a huge amount of patient data, both clinical as well as epidemiological data about these children. We have a very different study, which is called a cohort study, which follows about 3,800 children forward in time, and that's been going on now for 7 years. And so this allows us to look at the community base, and this allows us to look at the more hospital base. And so I'm going to focus first on our cohort study, where the primary goals were to better understand the spectrum of disease in children, to characterize natural dengue transmission, a big focus on investigating the immunological and the viral determinants of dengue and of severe dengue, and then eventually to develop a site for vaccine and drug trials. And so just to show you the kind of the study design and how that works out, which will be important for understanding some of our later work, what you see is that what we do is we take a yearly sample in what we call a healthy blood sample. So this is when the children are not sick. And what we do is we can look at the antibodies and the immune cells and gather clinical, epidemiological, and geographical data. And so what we then do is we measure the amount of antibodies from one year to the other, and if there's a 4-fold rise in anti-dengue antibodies, then we know that that child was infected during that year. In the meantime, we follow the cases. Anytime that there's a fever that reports to the clinic, we then take an acute and a convalescent sample, and we characterize that by febrile illness to see if that was or was not a symptomatic case of dengue. So from this, we then can measure the virus, the antibodies, the immune cells, and we can calculate the symptomatic cases, and then since we know the total number of infections, then we know that the total number of infections minus the symptomatic cases are the inapparent infections. And why that is important is that since we have the prior sample before all of those infections occurs, we can actually look at what is it about the either peripheral blood mononuclear cells, the B cells, the T cells, the antibodies that child had before the infection that might have protected some children from having any apparent disease, others from having mild disease, and then having others allowed to progress to severe disease. And this is what is a nice study that you can do within a cohort design. So just a couple things that are interesting just epidemiologically, and what we're looking at here is the incidence of dengue, of reported dengue in all of these different health centers, 21 health centers in the city of Managua, which is the capital of Nicaragua. And so what you see here are 5 years of our cohort study, and you see this is our cohort study. So it's not exactly like there was more dengue just around our particular health center. And in fact, we can show this because this is our same health center, but not the cohort children. It's simply that we are capturing the dengue that there is. And when we calculate this over this 5-year period, we find that there's about 20-fold more cases of dengue that occurred than are actually reported. Now this is really important when you build a case for a dengue vaccine or antiviral development, because it means that whatever number of the cost of the disease is actually needs to be multiplied by 20 to be able to understand what the true economic burden of this disease is. And it's not just Nicaragua, there's a number of papers that are coming out from around the world that have very similar numbers. Another interesting thing that we noticed, and what you're looking at here now, is the percentage of children with dengue, and this is age stratified, so 2, 3, 4, 5, et cetera, up to 12 years of age, that fit the case definition for dengue, as the WHO describes it, and those that do not fit the case definition but have no other diagnosis. And so we just call these undifferentiated febrile illness. So what turns out is that about 25%, so 1/4 of these children are not actually presenting looking like dengue. So it means that we're having another major underestimation of the amount of dengue. And in fact, in the smaller children, more of the cases don't fit the case definition. So in fact, probably because 2-year-olds are like, "Mommy, I have myalgia," but it also means that we're missing a lot of the disease in these young children. And so what we've been able to do is to establish this cohort and then be able to provide direct healthcare benefits, get important information for the Nicaraguan health organizations, and also as a basis for this immunological and virological research that I'll refer to in a few slides. But what happened was that we had this beautiful study design, and as I mentioned, this is how we do it, and we noticed that we had 80,000 consults from these children and 350 cases of dengue. So clearly there was something else going on, and for a number of reasons that I don't have time to tell you today, we started looking at influenza. We first did a retrospective analysis of what we call influenza-like illness, and we found that there was a large amount of illness that looked just like influenza. And then we started a 4-year prospective study to see whether there was in fact influenza in the tropics, because the going mantra at that time, which was about 4 or 5 years ago, was that there really wasn't much influenza in the tropics, it wasn't an important disease, and that there wasn't very much seasonality associated. And what you can see from our data on this is now laboratory confirmed influenza. This is in 2007, 8, 9, and 10. You can see a very distinct seasonality, and this is actually every June 1st, I kid you not, June 1st, we get our first case of influenza every single year. And this June and July is actually right over the peak of the southern hemisphere influenza, which is in essentially June, July in Brazil and Argentina. And then this other peak we see in December and November is right under the peak in the northern hemisphere. So for building pandemic models, it's actually really important now to take into account what's going on in the tropics, because this could be a really important area for understanding, and we're actually working with Mark Miller's group here at the Fogarty International Center to try and understand this. The other important thing is that we're able to confirm that the incidence of 21 influenza cases per 100 person years, which is almost identical to what is estimated in the United States. So this is considered to be a big problem in the United States, but not a problem at all in Nicaragua with exactly the same disease burden. So I think that this data has actually really made people start looking at influenza in tropical developing countries. So I just wanted to show some of the other work that we've done in collaboration with the Fogarty, which is to look at how these cases, whoops, let me go backwards here. Okay. So what we're looking at here is we're going to come up. We're trying to look at here. I don't know what this is going on here. Okay, so we're going to go, and this is Google Earth here. We're going to go down to Managua, and oh my God, this part makes me completely woozy. Okay, so this is where our health center is, right here, and what you're going to start seeing is from 2007 out to 2010, the different points are influenza A and B cases marked separately, and this is how they're coming up in the geo-referenced houses of our cohort participants. And as you come here to 2009, you're going to see that there's a different pattern in the H1N1 pandemic, which was much more in August than in any other year that we'd seen before. And then this year we had this very abrupt influenza A H3N2 outbreak, which you'll see here in yellow, and then followed afterwards by influenza B. So this is just seeing them across space and time. But what we're doing next is then to look at, this is now what they've done, and this is Vladimir Alonso from Mark Miller's group, and what he's done is now to connect them the closest temporal in a 2-week period and spatial interaction. So now you can start seeing the space and time interaction between the cases as they're connected. This is the same data as before, but now I'm showing it to you again in this form that connects the closest space and time. Again, here's our pandemic, H1N1, and then later on we're going to get to this year where we had that abrupt peak of the influenza A H3N2 in yellow, which was a very abrupt peak. So now what we can do in the next phase is that we actually have full-length sequence on most of these isolates from the genome sequencing centers here at NIH. And so we're now we're trying to combine the phylogenetic analysis with the space and time to see how that changes. And it's also now going to be the subject of further studies that'll allow a household transmission approach to looking at the serial interval and some other really important parameters that are simply unknown about how influenza is transmitted both in households and in the tropics. And so what we kind of, in just a very short amount of time, we were able to move from a place in Nicaragua where influenza was just not considered a major health problem, and there was a huge number of unknowns about it, to where vaccines are starting to become available. We understand the burden of disease. We understand that there's seasonal variation. We're looking at risk factors. We've documenting and sequencing the virus circulation, and so we've actually been able to move this whole program forward very quickly, having the base of that dengue cohort that we could then add on different diseases. And so we were also able to help a lot with the capacity building during that pandemic in 2009 that was initially identified in Mexico at the end of April, and by May we actually already had our colleagues in Nicaragua ready and able to do the protocols according to the CDC and the WHO, and actually the first case in the country was actually captured in our cohort just because of the heightened ability to monitor. And so where we're going now with this is that we're thrilled to have just received funding from NIH through the ICIDR program for a 5-year cohort on influenza, and then which will include household transmission studies. We're working with the CDC, which is funding us to do a birth cohort for 0 to 2-year-olds, continuing to sequence our viral genomes, and then through actually a different source of NIH funding through the RCE program, are working with Joe DeRisi's lab at San Francisco, UC San Francisco. We've actually already identified a novel enterovirus that has been circulating in respiratory samples. And we're also applying this technology to our dengue negative cases. So now what I wanted to do is to change a little bit, not only backgrounds, but also into some unpublished data, which is recent, and just some thoughts and ideas that we have right now. Because what happened during that same pandemic year was something really curious, where I don't know how well you can see this. This is just looking at all 6 of the years of the cohort, and you can just see over the epidemiologic curve that 1 year is very high, and that happens to be that same pandemic year. We had a really huge dengue epidemic in Nicaragua that time, and you can see this in our hospital-based study as well. And what happened was that we noticed that there was, and this is in real time, so we were able to work with the Ministry of Health to change the guidelines as this emerged, but a very curious atypical presentation of dengue with a lot of shock early on, which was actually called compensated shock, because it's poor capillary refill and cold extremities, and so it's actually not that what we call hypovolemic shock yet, but it was, and we actually had a couple deaths early on, and so they changed the protocol so that they actually were doing a lot of aggressive fluid treatment early on for these children, and in fact after that we got very little progressing to hypotensive shock. So, but it was very curious because you can see here, I'm just going to show a little bit of data, but this is looking at poor capillary refill, which means that when you take a child's finger or your own and you push on your thumb, for instance, it turns white and then it'll turn back red, and it should turn red within 2 seconds, and if there's poor peripheral perfusion, that'll take more than 2 seconds, and that's called poor capillary refill. But you can see in 2009-10, this was happening much earlier. If you do a Kaplan-Meier survival analysis, and this is with a hazards ratio, you can see that you actually get much earlier in 2009 than you do in the earlier years. It comes on earlier, and then you can also see what we call compensated shock, which is poor capillary refill and other signs of shock, also comes up again earlier by all of our different methods. And we see exactly the same thing in our cohort study. So we have 2 different studies, and we see the same early onset of these kind of shock syndromes, which are very curious for dengue. And so we did a lot of different analysis, but what I'm showing you is just one multivariate analysis controlling for, the secondary immune response to dengue serotype, age, sex, whether it was because they presented early, and the only thing that comes out highly significant is year 2009. So nothing else, we can't explain by all the natural things that we would explain dengue being weird, we can't explain it except something happened in 2009. And so this is, but we also was really curious is that in 2008 we had a huge epidemic of dengue 3, and 2010 we had another big epidemic of dengue 3, and we sequenced and it's all the same virus, and yet dengue 2008 and 2010 have typical dengue, and 2009 had this really weird phenotype. And so what we started thinking about, we actually had noticed a bunch of co-infections between dengue and influenza, both in our cohort and in our hospital study, which we published recently. And then what we looked at is if you look at, why was this clinical presentation different? Well, it's not the change in the viral sequence. The treatment and the fluid management could have affected the non-progression, say, to hypotensive shock, but it couldn't have affected the onset of these symptoms because that was before they came to the hospital. It wasn't the sequence of dengue infection because the secondary infection was not significant. And so what we started looking at was the epidemiologic curves. Since we have all this information about dengue and influenza from our cohort and also from the national surveillance, we see that the influenza, instead of being this peak in June, because of this pandemic year, it pushed into August so that it actually overlapped with the dengue epidemic. And we actually don't think that these are all caused by co-infections, but our current idea is it might be either a co or an infection close in time that might have an immunomodulation by the influenza virus infection of a very closely opposed dengue infection. And so our current thoughts on this is that, and we're actually looking right now and have some promising data, but I don't want to present it yet, looking at whether these children with compensated shock had antibodies specific to H1N1 influenza from those children that we actually have the samples from, to see whether this is actually something that we can prove in terms of whether A, they have the antibodies, B, whether there are higher viremia, C, whether they have actually what the levels of interferon look like, TNF alpha. And so we're actually looking at this in the human samples. But I got so excited about this that we're actually also setting up a mouse model of influenza and dengue to try and see if we can take a resistant mouse infected with influenza, and then after a certain time period infect with dengue and see if we get some kind of susceptibility. And so we're actually trying to set that up. And that is my lead into the next topic, which is our mouse model of dengue infection, which we have actually been working on for more time than my little dreams of influenza and dengue at the moment. But I wanted to tell you a little bit about where we've been going with the mouse model, both to understand the immune response and both in pathogenesis and protection, and then also look at possibilities for antiviral treatments via therapeutic antibodies. So I'm going to give just a little anecdote about this and then move it back out into the human infections and how we're trying to connect our work in the mouse in the laboratory with our work in the humans in the field. So what we work in is called the AG129 mouse model. It's a 129 background, and it's an interferon alpha, beta, and gamma receptor deficient mouse. So it is somewhat immunodeficient, but the good thing is that it can be infected with clinical isolates of all 4 of the dengue serotypes, and the infection is in relevant tissues, so it's in the spleen, lymph node, bone marrow, liver, peripheral blood, mononuclear cells, and we've also looked at which cell types are infected. And like in humans, where we've actually done studies both in children as well as in autopsy cases, we see in the same cell types as in humans, dendritic cells and monocyte macrophages. We also can show that the adaptive immunity is serotype specific and cross-reactive antibodies, and that there's a relatively balanced isotype ratio. And we're really sticking here to the humoral response, not the T-cell response in these studies. And we have a mouse-adapted strain that causes a lethal vascular permeability syndrome. And the only difference between this strain and its parent are 2 amino acid differences that essentially decrease heparin sulfate binding. It just means that the virus is not cleared as quickly and therefore remains in the periphery long enough to cause disease. And that's the difference, essentially. And so what we've done is we showed which we essentially wanted to use this model, among other things, to look and see whether we could prove or disprove this concept of antibody-dependent enhancement. So I showed you before in the beginning of the talk how this concept of one dengue infection leading to a more severe infection with a different serotype, but in fact everyone says that from the epidemiology, but no one's actually been able to prove that antibodies can actually cause more severe disease. So we thought, well, let's try and set out to do this. And so to do that, I need to explain to you what the concept is, and that is that since I just showed you or told you that the myeloid cells lineage is what is infected by dengue in humans and in our mice, we find that when there's no antibodies, you get a certain amount of infection. But when you have antibodies to a different dengue serotype, you still form an immune complex, but it doesn't neutralize the virus. And instead, the FC portion of that immune complex, the FC portion of the antibody, interacts with FC receptors, which are on myeloid lineage cells, and pulls the entire live complex into the cell and essentially increases the infection. And then you get a greater infection. And it turns out that the amount of viremia in humans, the higher the viremia, it does seem to be associated with more severe disease. And so what we can do is measure this in vitro, and I'm just going to explain to you what an in vitro, what we call ADE, or antibody-dependent enhancement curve, looks like. We do this by incubating dengue virus with the antibodies that we're interested in, and then we incubate this with cells that express an FC receptor, but not a dengue cognate receptor. So they will not be infected unless there is antibody present, okay? And then we do flow staining against an anti-envelope dengue protein. And what you see here is percent cells infection on the y-axis. And we see that if we have the anti-dengue antibody, as we dilute it, we get this characteristic curve where we get an increase in infection prior to neutralization. Neutralization, increase, and then just runs out of antibody. But if it's an irrelevant antibody, we don't see any curve. Okay, so this has been shown actually in vitro with a number of viruses. So you can show this with HIV, with feline leukemia virus and others. But in fact, why it's of interest with dengue is that it's thought that, for instance, in infants, we get a huge peak of severe disease. And the idea is that as maternal antibodies, which are passed to the child, will catabolize, that in the beginning they're neutralizing, and then over a 6 or a 9 month period, you get this big peak in severe disease as the antibodies wane, and then eventually there's not enough antibodies, so you don't see anything. And so that's what is thought is going on in humans. And so this is why we wanted to try and recapitulate this in mice. And so what we showed was that if you take normal mouse serum and inject the mice, wait 24 hours, and then do a number of different dose challenges, what you see is at high dose, this virus can cause a lethal phenotype, as I mentioned. And so this is a Kaplan-Meier survival curve, and we see that the highest dose causes disease and death, but not the lower doses, 10 to the 4th, the 10 to the 6th. However, if we take immune serum against a different dengue virus serotype, and we then pre-treat these naive animals, so pre-treat only with this antibody, and then come in with our dose, now all of a sudden, boom, we get this sublethal infection has now been converted into a lethal disease simply by the presence of these polyclonal heterotypic antibodies. Okay, so this was the proof that, in fact, antibodies can cause this lethal disease in this model. And in fact, they die. It's a good thing you can't see these, but this is this really nasty kind of fluid-filled abdomens, and it's this vascular leakage that we tend to see. And it's exactly identical. And so this shows you, and I'm not going to go through this, but we've shown that antibody alone can enhance disease, that the enhanced disease is associated with increased viral burden, and that the pathogenesis of this antibody-enhanced disease is identical to what we see with just the lethal infection. So we have the same cellular tropism, we have high serum cytokines like TNF, we see platelet depletion, and in fact, it's a similar change in viremia as we see in monkeys and in humans. So we think that this is a relevant increase in viremia. So now the idea was, can we prevent ADE using modified antibodies, and how can we use this model to better understand antibodies and disease and protection? And so I'm just going to go really quickly through a couple of ideas as to where we're going with this. So one idea was, well, in vitro, we've just said that the FC receptor is required for ADE. So if this is true in vivo, then an antibody that can't interact with the FC receptor should no longer cause ADE or any lethal phenotype. So initially we did is we just chopped off the FC portion of the antibody, which is called a Fab'2 fragment. And in fact, we obliterated ADE both in vitro and in vivo. But of course, that's pretty crude. I mean, there's a lot in that FC portion, so it felt like we really should try and do something a little bit more sophisticated. So we collaborated with a postdoc, Mike Diamond, who has a large program on West Nile and dengue, and he had a number of antibodies called E60 is one of them, which is a fusion loop antibody and neutralizes all dengue serotypes. And then he'd introduced a single mutation, which I'll show you in a moment here. There's a glycosylation site which is essential in the FC region of the antibody for interaction with the FC receptor. So if you make a single point mutant in the FC region of a recombinant antibody that knocks this out, first we humanized it, and then they knocked this out, and it's called an N297Q, and therefore there's no longer this site for glycosylation. What happens is that in vitro, what you see here is the mouse version, which causes ADE, and then we have the human, which causes ADE, and then the single point mutant, boom, no more antibody enhancement in vitro. So now the question is, will this no longer cause ADE in vivo? And so we showed that in fact it can no longer cause ADE just as setting it up. But now the question was, can this actually act prophylactically? Can you actually compete this essentially non-binding antibody with live antibody, with real antibody, and who wins? So what we do is we add both the polyclonal mix and the antibody at the same time, and then we have a sublethal dose. And what we find is that the non-modified antibodies are fully lethal, but then as soon as you introduce this one point mutation, you get protection. So in other words, it's strong enough to overcome this enhancing antibody. And so then the next question is, well, it prophylactically is fine, but no one knows when they're going to be infected with dengue, so we better see whether this can work therapeutically. And so what next we tried is that we essentially primed the mice with these anti-dengue 1 antibodies, and then we come in with a challenge, and then either 24 or 48 hours later, we come in with the modified antibody to see, after you've already are on the road to a lethal ADE enhanced infection, can this antibody do anything? And as you see, no treatment is lethal, and 20 micrograms after 1 day fully protects these antibodies, even though they're already in this essentially enhanced disease. And then we find that after 20 micrograms at day 2 also protects, but less so. But if we add a higher dose, then we come back up to a high degree of protection. So in other words, this could be some potential idea of how an essentially an antibiotic therapeutic might work. We also collaborated with a different group. I wanted to mention one thing. If we look at the same story, but instead of survival, we look at viral load, which is looking at essentially the viremia and at one of the serum cytokines that are really crucial for the vascular leak phenotype. What we see is that with no treatment and then with treatment, you knock down the viremia and serum and the small intestine and the bone marrow. So it's actually, not only is it no longer enhancing, but it's actually actively neutralizing the infection by pushing down the viral load. And it's also highly reducing the TNF alpha levels, which is what actually is mediating this inflammation and the vascular leak syndrome. So we actually have something which is we actually can see why it is that we are able to get the survival associated with this therapeutic antibody. We also looked at modified human antibodies with a different group. Federica Salusto and Antonio Lanzavecchia had done a similar modification, but this was of human antibodies. And just to make a long story short, the unmodified antibodies are no longer cannot protect therapeutically, but these modified antibodies, even when they're given after the infection, can actually come in and protect. So that's interesting. And the other thing that we said, well, that's after an antibody-dependent enhancement. What about if you just have a lethal disease and then you come in with this therapeutic antibody? Can it do something, or does it have to be in combination with this antibody dependence? And what you actually see is that both the ADE and the lethal disease, we have here lethality, but both of them are able to be protected by these therapeutic antibodies. So now we want to understand how it is that this is working. And so it's very interesting because we can look at a whole bunch of different antibodies that have different characteristics to see which are the best antibodies for this, so that we can, if someone's going to go forward with this, as people are trying to, into humans, you don't want to just try out some antibodies. You actually want to understand mechanistically why is it that these are working. Because we find out that some of these, I'm just going to talk about 2 of these antibodies, are highly, highly neutralizing, and yet only this E60 protects and these other ones do not. So clearly there's something about this particular antibody, and we're trying to understand what is it that makes some antibodies really good therapeutically and others not, because that is crucial to be able to move forward. So I just wanted to show you that what we're using this model for, we have a way that we can look at what types of antibodies enhance, and then we can also look at a protection model where we look at either a prophylactic situation or a therapeutic situation, and all of this we can actually play with different monoclonal antibodies and different types of serum. Because what we're really interested in, as we're using now, is a way to analyze human serum from different situations in humans and put them into the mouse. And then what we can do is we can actually remove different elements of that human serum to understand what is it in human serum that is contributing to protection and enhancement. We're actually using the mouse as a readout system because it actually works for both protection and enhancement. So all I'm going to do is show you one piece of data from that set of experiments. Actually, I'm just going to go through this because I've already told you about it. And so what we're really interested in now is characterizing the human polyclonal response. And we can do this at the serotype level, and this is a picture of the dengue virion. We can do this at the domain level and at the epitope level. So we can now try and really pull apart this immune response and try and figure out, not only in the mouse, but in the human polyclonal response, what's going on. And so the only thing I'm going to show you here is what we've done is we've taken serum from different infections that are in humans, and this is in collaboration with Aravinda da Silva at the University of North Carolina. And he has what he calls a traveler's clinic, where the students that are returning from their vacation in the tropics and got sick come, and a very large proportion of them actually have had dengue. And since we work in pediatric populations, so we have 5 mils of blood, but these students are like, sure, hundreds of mils, not a problem. And so he's got this amazing resource, which is human serum that can then be biochemically dissected and then tested. And so what we do is, we want to look at this cross-protection or this enhancement idea and put it into this passive transfer model. And the only piece of data that I'm going to show you is where we actually took human dengue 2 serum. So these are, as a particular person who was infected with dengue 2 as a primary infection, a different person was infected with dengue 3. And so what we do is we put this into the mouse, and then we actually do what's called an eye bleed, where you take a little bit of the blood out of the mouse and measure the neutralizing antibodies in the mouse at the time that you're infecting them. And then you do a dose here, and we're going to look at serum viremia. So now we put in this serum, we take it out, we measure the neutralizing titers, and this is against a dengue 2 virus. And you see that there's equivalent, this is a neutralizing titer on the y-axis, it's an equivalent amount of neutralizing titer, and this is normal human serum. So equal neutralization from a homotypic and a heterotypic infection. But now if we look at serum viremia, which is on the y-axis, the dengue 2 serum against the dengue 2 virus is able to neutralize a homotypic virus. But the dengue 3 serum against the dengue 2 virus is not able to neutralize it, even though it has the same neutralizing titer. Okay, so this is showing you that in the human antibody polyclonal response, what is contributing to protection are the homotypic antibodies and not the heterotypic antibodies. Okay, so this might sound super convoluted, but it's a big deal in the dengue field to try and understand what's causing the protection, and it's actually very important for vaccine development. We have wonderful vaccine developers here in the audience to understand what is really contributing to the protection. And then we actually did the same thing with an enhancement. And so I just showed you that serotype-specific human anti-dengue 2 monotypic serum can neutralize a homologous infection, but not as much the heterotypic. I'm not showing you the data, but we also could show that the monotypic serum was 10-fold less enhancing in vitro, and then we also see that it's 10-fold less enhancing in vivo. So we can actually look at these two sides of the coin, and we're starting to be able to really pick apart, as I said, at the domain level and the epitope level as well. So where we're going with this particular mouse model is to really define these both monoclonal and polyclonal characteristics. This is the therapeutic potential, and then the determinants of the protection and enhancement. We've actually have another project looking at the role of memory immune response, and we've actually been using this to test some potential antivirals just to move the kind of preclinical testing along. And so all of this is to really understand how to help develop a safe and effective vaccine as well as move along the antiviral. So it's got both a basic science component as well as a translational component. And I'm just going to end this talk by kind of showing you how we're trying to move out some of these back into the human populations, because I promised you we'd go back to Managua. And so what we're trying to do here is use the different types of study designs that we have in Nicaragua to ask different types of questions about the immune response, but this time in humans. And so what we have is essentially a hospital-based study that I mentioned earlier. So the way this is set up is that you have kids coming in when they're sick, and then we actually have a convalescent sample and we follow them out to 18 months. So we have samples out to 18 months. But what this allows us to look at is the question of the disease severity, because a lot of kids are coming into the hospital, so we have a high percent of severe cases, much more than, say, in our cohort study, which is from a community. So here we have maybe 25 to 40% of our kids have severe disease, so that we can really use as an outcome and have enough numbers to support the statistics. Now, a very different situation is with our cohort, where I told you we have these yearly samples, and then we have the acute and convalescent. But here, we can look at severity, but we don't have huge numbers. Here, what we can really look at is inapparent versus symptomatic disease, okay? So this now allows us to ask a different question. Do they get no disease at all, or do they get sick? And then we can actually also look at this question of repeat infections, where we now actually have about 100 and some infections, kids which have had multiple infections that we can document over the 7 years. And we can go back and really understand who's getting sick. Is a third infection just as bad as a first, second, third? So this is really important data for the dengue field. And then the last situation we have is also very interesting. This is based in the cohort. But what happens is that we have an acute phase sample that we confirm right away as positive. We go to their house, we bleed 25 contacts who are willing to sign an informed consent form, and then we actually can look at what's going on in these people that are, of their 25 contacts, we can see who is viremic, who has the dengue virus but isn't even showing any symptoms at all while they're viremic. So that's actually truly an asymptomatic person, what does their gene expression profile look like? What does their B cell profile look like? So we're actually looking at this in another situation, which is the asymptomatic and pre-symptomatic versus a symptomatic infection. So now we have 3 different epidemiological designs that allow us to ask 3 different types of questions about the immune response. And what we're able to do is look at disease severity, inapparent and symptomatic infections, long-term immunity, and repeat infections. And I'm not going to go into this, but we have this laundry list of approaches that actually have now all been validated to look at the human response. So we're looking at serum avidity, antibody repertoire, B-cell response. We have some really interesting data, actually, that's hot off the press, looking at avidity, which is essentially the force of the interaction of serum antibodies with the virus. And it looks like the sicker you get, so the more severe disease, the lower the avidity of the antibodies, which is something you might, meaning that the antibodies are less functional in the people that have more severe disease. And so so this is something that we're just starting to work out. So just to give you a sense of kind of where we're going with that. So the conclusions of all of this was to show you a little about the epidemiology of dengue and influenza and to get out what kind of emblematic of a tropical developing country. To explain to you our ADE model of disease in our dengue model, to show that when you eliminate this Fc receptor binding, we can eliminate ADE, and that we can actually use this to develop therapeutic antibodies and then dissect what it is that's actually contributing to the mechanism of action. And then we've also shown how we can then use this model to kind of pick apart the human polyclonal response in the mouse, as well as being able to then bring it back out into the analysis of the human polyclonal response by this whole set of different approaches that we're just now starting to roll out. And so all I'm going to do is end with a couple words from our colleagues in Nicaragua, because I can tell you what this means to me as a scientist in the United States, but I wanted just to see if I can get a couple words and end this talk with, first, just a couple words from the different people that I work with in Nicaragua about kind of what this has meant for dengue research in Nicaragua, and then, if I have time, a little piece about rolling it out from the science. So this is, I'm just going to roll this and see if we get some sound. Okay.
Lo importante de este estudio es que nosotros tenemos la dicha de conocer si realmente el paciente tiene dengue o no en 24 a 36 horas de haber ingresado, porque se le tomó una muestra aguda, se manda al laboratorio y en poco tiempo nosotros tenemos ese resultado, lo cual nos ayuda como clínico para ver y distinguir qué paciente realmente es dengue y qué paciente no es dengue.
Realmente es un proyecto de que ha apoyado mucho al hospital en relación a la capacitación, a los recursos tanto técnicos como a la organización en sí de la atención del paciente. Además de eso, hemos tenido la oportunidad de hacer los estudios y además de esto sacar a flote lo que hace Nicaragua.
En el momento creo que nosotros fuimos pioneros, se podría decir, en la aplicación de técnicas moleculares en una epidemia de dengue. El laboratorio pasó a ser de un laboratorio prácticamente desconocido a una institución de excelencia en la región.
And if I have time, do I have another like 3 minutes? Because what I wanted to show you is kind of what happens when you go in, and you'll see the first part of this is just showing you the cohort study and then the kind of informatics tools that we used for the study, but then how they actually were used by the Ministry of Health then to actually start addressing the larger public health problems in Nicaragua, which is actually, I think, something that's one of the most important parts of our interactions with colleagues in global health. So I'm just going to do
Eva
this.
Harris explains the goals of the study and how technology played a key role in its running.
The cohort study stated goals are to describe the natural history of dengue transmission in a pediatric or children population. Another stated goal was to collect high-quality biological samples and epidemiological information to accompany those samples in order to be able to follow these 4,000 children in a place that doesn't have any addresses or landlines for phones. This incredible informatics system was set up by the Nicaraguans to be able to essentially track the children and to be able to deliver their health care in a more effective manner.
Nathan Joswiak describes the quality and the importance of the cohort study's technological infrastructure to the research that comes from it.
The infrastructure that they have in Nicaragua is really incredible. Maintaining the samples, keeping track of the patients, it's really advanced, and it has to be because there are 4,000 kids in this study. And when the samples work their way through the pipeline, it's essential that everything is properly organized. It's an essential part of science. It's something you don't think about, but when you're doing such high throughput work, when you're looking at so many samples, organization is key.
One of the main challenges in the cohort study was locating families in the poorest of Nicaragua's barrios. Miguel Reyes, an epidemiologist and nurse at the Ministry of Health, explains how this problem was solved.
Nos encontramos en el barrio Santana Norte, en el asentamiento llamado Brisa del Solotlán, donde tenemos niños de la cohorte pediátrica de dengue, donde hay una buena cantidad de niños de todos los grupos de edad. En este sector de aquí hay lugares donde no tenemos nosotros un punto de referencia. Por lo tanto, para cuando se quieren hacer visitas, nosotros hacemos uso de la tecnología. En este caso nosotros estuvimos utilizando el sistema de posicionamiento global, que es el GPS, que nos sirve a nosotros para puntualizar y georreferenciar cada domicilio de los niños que forman parte del proyecto de dengue.
William Aviles Monterrey, Head of Information Technology at SSI Nicaragua, describes one way in which the data gathered from the cohort are now being used.
Desde el punto de vista epidemiológico, hay muchos datos que utilizamos normalmente para lo que es la vida diaria en el centro de salud. Primeramente, por ejemplo, en lo que es control de casos de dengue. Entonces utilizamos la informática para determinar qué área está en riesgo de ser más afectada por una epidemia de dengue. Utilizamos mapas, utilizamos datos estadísticos y utilizamos tendencias para determinar dónde se necesitan más acciones de control.
Dr. Guillermina Kwan, director of a Nicaraguan health center, explains how the technology infrastructure put in place for the dengue cohort study is now being repurposed for other uses.
Ha sido muy provechoso el tener la cohorte de dengue y sobre todo el aprovechar, ¿no?, de la tecnología de implementación del estudio. Aprovechamos esta herramienta informática de tal forma que cosas que antes las hacíamos en 6 horas, como es un día de jornada de vacuna, el procesamiento de esa información ahora la tenemos resultado en 1 hora. Entonces eso es ahorro para el mismo sistema y menos trabajo también para el personal de salud. Entonces hemos trabajado a la par esas herramientas de embarazada y las herramientas de vacunación y el poder tener un registro de las vacunas aplicadas a los niños. A medida que tuvimos estas herramientas, compartimos las mismas con otros centros de salud que han querido apropiarse de ellas para mejorar su trabajo. Bueno.
So this is I just wanted to give a little sense, it's not specifically about dengue, but kind of how we've been able to really partner with the Ministry of Health to move out beyond the studies into helping all kinds. In fact, our SSI, my nonprofit, has an office there, and we have 15 people in the informatics team, which has now kind of expanded and is getting all kinds of their own grants to help the Nicaraguan and actually Guatemalteco and other other countries in the region to essentially do needs assessment and establish the informatics to support public health goals. And all that kind of grew out of this whole project in a way that I never would have dreamed. So I just want to thank the people who, this is my molecular virology team, and then the people now in the past who've worked on the immunology, the mouse work that I told you about, especially Kate and Scott, Robert and Simona. And then this is just some of the few of the people in Nicaragua at the Centro de Salud, the health center that you saw, the hospital, Dr. Angel Balmaceda, who's a fantastic director of virology there, our sustainable sciences, and a lot of support from the Ministry of Health, especially Alcides Gonzalez. And I also wanted to acknowledge my collaborators here in the States and in Europe, and also wonderful people that I've been working with for a long time here at NIH, particularly Christina Cassetti and Kathy Laughlin from DMID and the virology branch, the Fogarty International Center. We have a really wonderful collaboration with Vladimir Alonso, Cecile Vivo, Martha and Mark Miller. And then we're very excited to start our work with ICIDER, with our program officer Diane Post. Robin Mason is coming down to Nicaragua next week to do our assessment And then it has really nice graphics, and the videos were from HHMI, and I want to acknowledge them. Of course, the funding from NIH, WHO, and the PDBI, and thank you to the children and to you. Sorry, I went a little bit over. I'm not used to these videos.
Thank you, Eva. I mean, it's exciting to see the wide spectrum of your work from the bench to the bedside and to populations, public health, and training, and even building that capacity, not only in Nicaragua, but surrounding countries. But we have time for one or two questions.
Yes.
Hi, Eva. Mike Bray. A couple of questions about your mouse model. This is NIH, so of course we care about mice here. Do you have a mechanism for measuring vascular permeability other than Evans blue dye? And are you testing any mediators that modulate vascular permeability?
Yeah. So actually, no. We rely on the Evans blue system. And in terms of the mediators, the work we had done was looking at TNF alpha particularly, because it's pretty generic, but it actually has been implicated in humans as one of the key mediators of the vascular leak we see, at least end-stage inflammation. And so what happens in our model when you deplete for TNF alpha by adding antibodies, you actually you obliterate that early death phenotype. So it actually is important for you. You get this delayed paralytic, but when you deplete TNF alpha, you no longer get that vascular permeability phenotype.
Okay, but are you going after the endothelium itself and its response?
Yeah, so we aren't focusing that much right now on it. Partly, there's a number of other groups that are working. I should mention also Susan Shrestha, a former postdoc, independently actually came up with this model, and she's shown some endothelial cells, LSECs in the liver that might be important as well. We actually are not exploring the pathogenesis in the model as much. I just kind of, because it's a mouse model for a disease that affects humans, I feel like, I just acknowledge what the limitations are and what I feel that we can really learn from the system, which I feel like we have a system for looking at the antibody right now. And then, but we've thought about going after it, but we're not actively pursuing that right now. The pathogen, like the actual mouse pathogenesis per se. But you had a question.
Yeah, I guess I need to go. So I wanted to ask you about the 4 species of dengue in the field. You said there are 4, but it seems like in Nicaragua anyways, that 2 of the 4 are the ones that are infecting people. What about the prevalence of the other 2 species? And is there varying abundance of them? Why only the 1 and 3 infect people?
Yeah, no, it's not. No, 2. It comes in waves. It just depends on what you see is in all dengue endemic areas. Well, it depends. Bottom line is that in Nicaragua, all 4 will cause disease. It's just that the period of time, like when we started this particular study, it was dengue 1, and then dengue 2 came in, and then dengue 3. In 1998, or when I had it in 95, it was dengue 3, and then it was dengue 2. So it just goes in waves. In the newly endemic countries, in the kind of hyper-endemic countries like in Asia, all 4 serotypes are going on all the time. Interestingly, even when all 4 are going on, you get a biphasic interaction with dengue 4 seems to be out of phase with dengue 1, 2, and 3. It's something which has been noticed by phylogenetic analysis. But anyways, the bottom line is that all 4 are there, and it just depends, because you essentially will, the population will get immune after a lot of, say, dengue 3 circulating, essentially you'll no longer get a lot of dengue 3, and then you'll have dengue 1 come in, boom, big, and then it goes in these waves that are kind of driven by the immune response of the population. Yeah, yellow fever is not a risk in Nicaragua yet. Interestingly, in Brazil is where there are some cases of urban yellow fever, and there's a lot of watches out for that, but it hasn't actually exploded like we thought it might. And there might be some kind of cross protection, as I also think with West Nile. I feel like I think there is a cross protection from having just a ton of dengue antibodies that might be protective against other flavies. Is my pet hypothesis. We can go into that later, but I have no evidence to prove that. Yes.
One last question.
Yeah. Is there any difference among the serotypes in their propensity to do things like cause CNS disease? Once in a while, you can get dengue encephalitis with seizures and so on.
Yeah, absolutely. I don't know. There are a couple cases of dengue CNS disease, and I don't think that there's enough that have actually been able to do an analysis of the serotype. We looked at serotype-specific differences in, for instance, ability to cause shock, and first of all, definitely dengue 1 and 3 will cause primary disease more than dengue 2 and 4. So 2 and 4, you will almost never see severe or even symptoms in a primary case. We've also found that dengue 2 actually progresses to shock faster than dengue 1, that dengue 1 had more, so we were able to pull apart some things, but they all overall can cause the same thing, but there's definitely flavors. I mean, like clinicians will tell you, this is dengue 3, so there's something about them that is distinct, but it's hard to put the finger on it.
Thank you, Eva. I'm asked to remind you that...
Okay, thank you.
So we have refreshments out back, and I'm just asked to remind you that we have 4 types of cookies, and if you take a cookie, make sure you follow it up by the same cookie, otherwise you'll explode. Coffee might mitigate that. Thank you. That was great. But I couldn't help it.